Hello, am I audible? Is the screen visible?
Everything is fine.
Okay, great. Hey everyone, welcome back. Hope you enjoyed the previous session on quantum physics. So today we're going to be doing a session on quantum computing. We'll be using some of what we covered yesterday, in the last session, but even if you missed it by chance, it's okay. You can still understand a good proportion of this session. If you did, you'll be able to get a lot more insights into today's session. Okay. So today we're going to be exploring quantum computing. I'm guessing it's going to be pretty new for most of you. Some of you might have seen some quantum physics in first year courses or elsewhere, but I'm guessing quantum computing will be pretty new. And even though it's just 2.5 hours, we will be able to actually see quantum gates, qubits, and some actual algorithms that can perform faster than classical computers and can do things that classical computers cannot. So it's going to be pretty cool, and I hope you enjoyed today's session. So with that, let's get started. So the things we will be covering today are, first off, we'll introduce qubits. We've already seen sort of a qubit in a spin-half system, and we'll look at a cool method of how to visualize these qubits. Then once we're comfortable with a single qubit, we will look at multiple qubits, and the way we describe multiple qubits will be through something called tensor products. That will be the main mathematical part in this session. Then the third part is something called Schmidt decomposition, which is a way to understand multiple qubits. And we will also look at Bell states, which are certain important states. We saw one of them at the end of last session. We will introduce them more formally and use them a lot this session. Then after that, we will move on to quantum gates. And then after that, we will go on to a couple of interesting examples. One is quantum teleportation. Along with that, we will also do something called superdense coding. And once we're done with those two, we will look at an algorithm that a problem that quantum computers can do faster than a classical computer, which is the Deutsch problem, and the solution being the Deutsch algorithm. After that, we will just touch upon what is the requirements to build a quantum computer, and we'll look at a couple of examples and what the current situation is. This will be very brief, and that it's a field of its own that requires complete exploration. And I don't want to spend too much time on this. Is more about the theory of quantum computing, but it's very interesting and you can look into it yourself later. And lastly, since we have been doing 2 sessions on quantum physics, I thought we'd finish with something slightly philosophical in Bell's inequality and about the thought process and the unusual nature of quantum mechanics and what puzzled a lot of people, including Einstein. All right, so that is the plan for the session. And let's get started. And also, in case you missed the last session, my name is Sai Subramanian. I'm just finishing my BSMS physics at IIT. And yeah, let's get started. So we start with defining qubits. So in classical computing, we store all of our information in terms of bits. The classical bit can either be in the state 0 or 1, and one bit stores one binary information. 8 bits make a byte, and then we have kilobyte, megabyte, so on, and we store a lot of information like that. So similarly, our fundamental unit of information in quantum computing is the qubit. So the qubit can be in any superposition of the 0 and 1 state. What are the 0 and 1 state? It depends on what kind of quantum computer we're building. And whenever we do the theory of quantum computing, we don't care. Basically, we just assume there is a 0 and 1 state and we build the theory. Okay. So one nice example for us is a spin-half system. A spin-half system can behave like a qubit. So that is sort of why when we were doing a spin-half system, instead of using the notation plus half minus half, I use the notation 0 and 1. So that all of you are already comfortable with quantum computing notation, and any calculations that we do now, the notation will just continue, and I hope it's more comfortable. Okay. So in case you missed the previous session, this is just called the Dirac notation, and the brackets around the 0 is called the Ket vector, and that is just notation we use to describe a vector. Okay. So psi is a times 0 plus b times 1. A and b are complex numbers. And we want normalized state vectors. So mod of a squared plus mod of a the whole square plus mod of b the whole square is equal to 1. So that is the only restriction in the state of a qubit. So writing a qubit like this, we can sort of get an idea about it. There is a different way to write a qubit, which gives us some nice intuition into what the qubit is doing. And that is in the form you see below. So what we have done is, since mod a whole square plus mod b whole squared is equal to 1, we know that we can write the magnitudes as cos of an angle and sine of an angle. So we go with cos theta by 2 and sine theta by 2. But of course, a and b are also complex numbers, so we need to put two phases next to 0 and 1 to adjust for that. And an interesting fact about qubits is that the global phase of a qubit, that is the phase that you see outside, sorry about that. Yeah, this guy here, that is, it is not the relative phase between the amplitudes of 0 and 1. It is a global phase multiplying the entire state. This guy does not influence any single qubit measurements or gates or anything. Because whenever we take a measurement, we will be taking inner product of something with psi, and then we will be taking mod of that inner product's square for probabilities. So whenever we take that, we will get a z bar situation where we will get an e power I gamma, e power minus I gamma, and these two will just cancel. So because of that, this gamma and the global phase of a qubit doesn't matter. And so because of that, we can just define psi in terms of two numbers, theta and phi. Why do we define theta by 2 and not phi, you might ask? Well, there are a few reasons, and you can see them immediately when we look at how we are going to visualize this. So in this notation, since we have only two numbers, theta and phi, the way we visualize theta and phi in math a lot is using a unit sphere. And so we will be doing the same here. So this unit sphere is called the block sphere. So based on the value of theta and phi, you can draw the vector, and that is our state. So all the possible states of the system are all the different values of theta and phi on this sphere. So the first and simplest state, that is 0, is just the z-axis, the positive z-axis, which we can see by theta equal to 0 and phi equal to 0. Yeah, and similarly, we have the one state here. And if we have an amplitude, we can similarly have sine theta by 2 with the amplitude on the xy plane. And depending on the angle phi, it's either the x or the y. And if you remember the states we defined for spin half systems, we defined an x plus state, which was 0 plus 1 by root 2. Okay, so if you don't remember, just or you didn't attend the previous session, just take this for granted. This was the state with definite spin plus half in the x-axis. And if we see how we get the state is nothing but theta equal to pi by 2 and phi equal to 0. We can substitute and see. We will get cos of theta by 2 cos pi by 4, which is 1 by root 2 times 0. And we get sine of theta by 2, so sine pi by 4, and e power I phi is 0. So we get 1 by root 2 times 0 plus 1 by root 2 times 1, which is nothing but the x plus state. And if you put theta equal to pi by 2, we know we are on the xy plane, and phi equal to 0 means we are on the x-axis. So you can see that our definite x plus state is the one pointing in the x-axis plus direction. The same will be the case for x minus, same will be the case for y plus and y minus states. The y plus and y minus states will point in the positive y and negative y axis directions. So you can really see the relation between the spin half and the qubit representations. And this is why we use the definition of theta by 2 to make that mapping definite and to have this visualization. So this sort of visualization, while very cool, unfortunately does not generalize to multiple qubits. We don't have any sort of visualization like this for multiple qubits, but it's still very nice to sort of think of an individual qubit and all the states it can have. Okay, so that is on individual qubits. Just to summarize, any superposition state of 0 and 1 and the spin half system we saw yesterday, all the intuition, sorry, in the previous session, all the intuition we derived on that, all of that holds for a spin half system. Okay, so now we will move on to multiple qubits. We touched upon this at the end of last session because I wanted to give you a hint of what we'll see today, but we will do it a lot more formally now, and this will lead us to the only time we will dive into proper math in this session. Okay, so we will be touching upon tensor products. So I know the word tensor and tensors might scare a few people. It did scare me when I was doing topics. I did not want to do a lot of tensor algebra, but tensor products is not really tensors as such, and the way we will be using them will more be using only vector logic. Okay, so we will not be going too much into the tensor logic and be using special methods from there. It is more a means to an end for us, but we will define this in general, and I will tell you just what happens in a 2 by 2 column vector space, which is the qubits we're dealing with. So in case you're not comfortable with the general definitions, just stick to the example, and that will be enough to understand this session. Okay, so how do we define a tensor product space? Let's say we have two vector spaces, V and W. The tensor product between these two spaces is a new vector space. So okay, we have some new vector space. We call that V tensor product W. And this new vector space is the space of all possible linear combinations of the tensor product of its individual elements. And that might sound weird because we haven't defined what is the tensor product of individual elements. We will do that here. So the tensor product of two individual vectors is just a new vector that represents what those two individual vectors are. So if you look at the tensor product of two individual vectors, say we have the 2D column vectors example again. We have B1 is equal to A1, A2. We have W1 is equal to B1, B2. So V1 tensor product W1, this is how we will write that. And we are pretty lazy, so sometimes we will just write it like this. And we are sometimes very lazy, so we will ignore that as well and just write the state like this. All these three mean the same. And what this just means is V1 vector is in the state A1, A2. W1 vector is in the state B1, B2. This is shorthand to represent that. That's it. Nothing special happening. Just telling us that V1 is in the state A1, A2. W1 is in the state B1, B2. That's all this means. Now, sometimes we want to write it in the new vector space. And the way to do that mathematically is we multiply each element. So V1, W1, we can define like this. This just means V1 is in this state, W1 is in this state. The way it is written in actual mathematics as a single vector, since I told you this is a new vector spaces, we take the first element of the first vector A1, and then we multiply it with B1 and B2. So that gives us A1, B1, and then A1, B2. After that, we take the second element from here, A2, and then also multiply it with B1, B2. That gives us the third and fourth element, which is A2, B1 and A2, B2. Okay. I don't have enough time to like completely motivate this definition, but think of it like this, that if we are going to do something with this vector, then we want the same logic that we had for individual vectors to hold, and this sort of a definition lets that happen. Okay, so just take this definition for granted. Otherwise, that if you want to write this as the individual vector, it is take the first element, multiply by the two elements of the second vector, and then take the second element of the first vector and multiply by the two elements of the second vector. So we can do the algebra of multiple qubits either using this simple form where I just write it as V1 tensor product W1, or we can write it as the actual 4D column vector. We can do either. And sometimes we will work with the former, sometimes we'll work with the latter, depending on what is comfortable later. Okay, but both of these are exactly the same thing. It just means that the V1 is in the state A1, A2, W1 is in the state B1, B2. So just remember that. And the vector space is called V tensor product W, the new vector space. It is a 4D column vector space, and it is all such linear combinations. Okay, so we can take any such vectors. We can take any vector in the V vector space. We can take any vector in the W vector space. Take the tensor product, which is just this in that state, that is in the other state, and take any linear combinations of them. And all of those are now possible states of 2 qubits. Okay. Maybe I think you might understand this a bit better if we explain basis. So the way we define a basis for our new space is taking tensor product of the basis vectors of the individual vector spaces. So for our individual vector spaces, we have I cap and j cap. That was our basis vectors. So we will now define 4 basis vectors for our new space. I1 tensor product I2, which just means the first vector is in I, the second vector is in I. So now we have 1, 0, tensor product 1, 0, and that gives us 1, 0, 0, 0, 0. So this is one basis vector. Similarly, we can take other combinations. You can take I in the first and J in the second. So that will give us 0, 1, 0, 0. Similarly, J in the first, I in the second, and that gives us 0, 0, 1, 0. J in the first, J in the second, that gives us 0, 0, 0, 1. So these are the 4 basis vectors in our new space. So if we are writing a new vector in our 2D space, let's say some vector D. This is a vector in a 2D space. We will write it as some alpha 1 times 1, 0, 0 plus alpha 2 times 0, 1, 0, 0 plus alpha 3 times 0, 0, 1, 0 plus alpha 4 times 0, 0, 0, 1. So this is a general vector. Yeah, this is a general vector in our new tensor product vector space. So if there is any 2 qubit system, this is how a general vector will look like. And what does this mean? It means that the probability amplitude of being in the state with first qubit in I, second qubit in I is alpha 1. The probability amplitude of the first qubit being in I, second qubit being in J is alpha 2. The probability amplitude of the first qubit being in J, second qubit being in I is alpha 3. And the probability amplitude of the first qubit being in J, second qubit being in J is alpha 4. So that is what this means. That is how we understand a 2 qubit vector. And that is why we have a 4D column vector space. And the dimension is 4. It's the product of the dimensions of the individual vector spaces. So this is tensor product. Okay. If it feels slightly confusing, don't worry. Just remember this definition. And the earlier way of writing them like this. Those are the only 2 things we'll need. We will either write them as just like this, like V1 tensor product W1 and do our algebra directly, or sometimes we will write them in this form, where we'll write them as 4x1 column vectors. That's all we'll be using tensor products for. Okay. So once we have our tensor product space, we define a dual basis for this space because it's also a vector space. And like we defined earlier, our dual basis is just this, the same vectors in row form. And they have the same meaning as the earlier basis vectors. And similarly, we defined a dual vector for 1 qubit systems. We defined dual vectors for multiple qubit systems. So it is the same coordinate vector, only thing we take a complex conjugate. Let's see an example to just see what that means. Let's say we have V1 defined like this, V2 defined like this. And we want to find the dual vector of V1 is the same vector. Take a transpose to make it row, but take the complex conjugate. So I becomes minus I. Okay. So that's it. Just take complex conjugate and transpose, we get the dual vector. And now that we have our dual vectors, we can define something called the inner product. complex inner product. Same as we saw last time, just multiply the dual vector and the second vector in normal matrix algebra, and that gives us the inner product. Okay, so we have our vectors that represent two qubit systems. We can define corresponding dual vectors and we can take inner products. Okay, so remember how I said that we can also deal with these vectors as just v1, w1, etc. Suppose we're doing that, how do we take inner product? So then inner product of v1, w1 and v2, w2 is just the inner product of v1 and v2, inner product of w1 and w2, and the product of those two. Okay, so just take individual inner products for the individual qubits and then multiply them. That will give us the inner product of the combined states. I'm not proving this, but if you try to write it down and see the algebra, it will just pop up immediately. Okay, so these are a few elements, these are a few properties of tensor products. What it basically says is tensor product is like distributive over like scalar multiplication. If you multiply z, you can just spread it. You can multiply, as in you can multiply. No, distributive is the wrong word. I'm sorry. It's associative. You can multiply the scalar onto the first vector, or you can multiply the scalar onto the second vector, or you can just take it out. That's the first property. The second property is distributive. So if you want to add two vectors in the first space and then take tensor product, it's the same as taking tensor product and then adding. So that's the second property. And the third property is the same, but for the second vector. So if you're taking tensor product of one vector and with the sum of two vectors in the second space, it just distributes. And we get v tensor product w1 plus v tensor product w2. These are all linear operators, so all these linear sort of properties will hold. Okay. So now that we have defined tensor products, I am going to give you the postulate for general composite systems. I've been explaining the tensor products with the example of 2D column vectors and qubits, but this idea of tensor products and for the combined space is the same way we will operate for any quantum system that has more than two or more components. So the postulate is the vector space of a composite system is the tensor product of vector spaces of the component systems. So if you had like 2 or 3 particles, each with their own vector space, you take tensor product of all those vector spaces. That is our new vector space for the composite system for any general quantum system. Okay, not only qubits, this holds in general. For us, we have seen what the tensor product space of 2 qubits looks like. We've defined the dual space, basis, and the inner product. So we have all the tools we need to understand 2 qubits and 2 qubit systems in general. Okay. So now the next topic that we will be covering is called the Schmidt decomposition. So this Schmidt decomposition is a way to understand 2 qubit systems better. But I will also tell you that this is not very important to follow the rest of the session, and it might look very different for people who have not done a lot of linear algebra. So stay with me, try to understand this. If it seems a bit messy, you can look at it later. It is not essential to understand what follows. Okay, after we cover this part, the linear algebra math will reduce and we will go on to just defining gates and doing computations. Okay, so but still try to understand this. It's pretty cool and it gives you a real intuitive sense of what is happening with 2 qubit systems, like what is actually happening. So consider a system of 2 qubits. So if we have a system of 2 qubits, typically how do we write them? We write them as alpha. Okay, let me use the notation alpha 00 times 00 plus alpha 01 times 01 plus alpha 10 times 10 plus alpha 11 times 11. So this is how we would write a general vector based on its probability amplitude with 00, with 01, 10, 11. This is how we wrote it earlier. So yeah, this is the same thing as what I'm writing below. But then this has 4 different numbers, and it doesn't really tell us what is happening to these 2 qubits. Is it like these 2 qubits are just separate and we're just thinking about them together? Are they entangled together? We just touched upon what is entanglement in the previous session. So are they relating to each other, or are they 2 separate entities and we're just thinking about them together? What is happening? So we want to really know that, because that tells us about our system. Do we need, if we make a measurement on one, what is it going to impact the other? What is going to happen? So we want to write it in a form where we can see that very immediately. So the way we do that is the Schmidt decomposition. So if we take psi is this general state that I just defined, we can write psi in the form sum over lambda, sum over I. This just I is just 1 or 2. Okay, so just two sum over 2 elements, lambda I, IA, IB. So what are these? So lambda I is nothing but a non-negative real number. So lambda I is a real number greater than or equal to 0. So you can think of lambda I as some square root of pi. It is a square root of a probability. It's a real number, positive number, okay? And that is what it sort of means. It's the square root of a probability. So if you take lambda I squared, think of it as some sort of probability of I. And now what is IA and IB? IA and IB are 2 sets of orthonormal states. It can be the same states that we are dealing with. It can be 0 and 1. It can also be some other orthonormal states, say the x plus and x minus, 0 plus 1 by root 2, 0 minus 1 by root 2. And IA and IB can be 2 different things. For example, IA can be this and IB can be this. They don't have to be the same orthonormal states. And that gives us a definition. So what this is saying is it has some probability square root of pi times some state. Let me just write it out as a sum itself. Yeah, let's say it is p1 times square root of p1 times some, let's say 0 and 0 plus 1 by root 2 plus square root of p2 times 1 and 0 minus 1 by root 2. So what does this mean? It means that with the probability p1, it is in the first qubit is in the state 0, the second qubit is in the state 0 plus 1 by root 2, and the probability p2, the first qubit is in the state 1, and the second qubit is in the state 0 minus 1 by root 2. So that is the meaning of this decomposition. Okay, and how was it different? How did we go from like 4 numbers to 2 numbers? Well, the reason is that our choice of basis was fixed. It is our standard basis. So we are taking 2 of our like free degrees of freedom and using them to define a new basis. That is how we got this. So it can be any basis, but if we choose a good basis that is natural to the set of 2 qubits that we have, we can write it with just 2 numbers. And we get this definition. There is a proof for this, but I am not going to do it in the session. We'll give you a reference textbook of quantum computing that will have the proof for this in case you're interested. The proof is basically stating the singular value decomposition. This is a theorem in linear algebra. If you've not heard of it before, it's a very awesome theorem used all over the place in all sorts of math, particularly math modeling and stuff in machine learning and other fields. And the textbook has a proof of the singular value decomposition and then a proof of this using the singular value decomposition. So we just mentioned the textbook at the end, and if you're interested, you can go through it there. For now, you don't need the proof. And again, this is just for intuition. We will not use this form too often either. So just to say, if we have 2 qubits, we can understand it as a square root of p1 times first qubit in one particular state, the second qubit in another particular state, plus square root of probability times the first qubit in the second orthonormal state, and similarly the second qubit in its pair orthonormal state. So this is a way to understand 2 qubits, and some terms and notation to interpret what this is. So the number of non-zero lambda i's is called the Schmidt number. So this Schmidt number can be either 1 or 2 because we have P1 and P2. If one of them is 0, it is just 1. If it's 2, if both of them are non-zero, we have 2. If Schmidt number is 1, for example, P2 was 0, we would just have square root of P1 times 0 plus 1 by root 2. That means we have a product state. That means we can write our state psi as psi1, psi2. And what does a product state mean? It means that psi1 and psi2 are basically independent right now. So this qubit 1 is in psi1, qubit 2 is in psi2, and doing a measurement or a unitary transformation of psi1 does not affect psi2, and similarly doing a unitary measurement of psi2 does not affect psi1. So that is a product state. It means that while they're in the same system, they don't affect each other directly yet. They're just in their own individual state and we're writing them together. But if Schmidt number is 2, it means there is some entanglement. It means we have to write it as a sum of two individual, like the way we wrote earlier, like this. And that means it's not a product state. It means that if we do some sort of a measurement on one qubit, or we do some sort of unitary transform on one qubit, so if you do a measurement on the first qubit, it will impact the second qubit. These two qubits affect each other directly. That's the meaning of entanglement. We saw an example last time and we sort of thought of its philosophical implications. Pretty cool. And yeah, so Schmidt number 2 is the set of Kohler states that are actually involved. For the Schmidt number 2 is where it makes more sense to actually write them together because they affect each other. That's the only way we can analyze them. We cannot analyze them separate of each other. And that happens for Schmidt number 2, and that is the sum and the way we write it here. And this tells us there is entanglement. If we want to know how much entanglement, that is how much one state affects each other, whether it affects strongly or whether it's a small change, we calculate something called the von Neumann entropy, or it's also very often called the Shannon entropy. So if you've done any information theory or quantum information theory, you will have heard this Shannon entropy. Quite likely you would have heard of the Shannon entropy. If not, for us is just a way to see how much entanglement is there. So the larger this entropy, the more entanglement there is. So the way we define this is just in terms of Schmidt numbers. Doesn't matter the basis we're using, and it is just minus sigma over the two I values, lambda I squared log of lambda I squared. So why this definition? Well, it is motivated by information theory. I'm not going into that there, but I'll give you a couple of examples to see why it works. So let's say we have a product state. I told you product state, the two qubits have no entanglement. So let's say lambda 1 is 1, lambda 2 is 0. So then it is a sum of minus 1 log 1 and minus 0 log 0. So this goes to 0, log 1 is 0. And this, while it seems like 0 into infinity, if you take the limit properly, that is 0 limit extending to 0 x log x, this will also go to 0. So the total entropy is 0. No entanglement, so S is 0. Whereas if we take something with the maximum possible entanglement, which is lambda 1 equal to lambda 2 equal to 1 by root 2. If you recall the Bell state from last time, 0, 0 plus 1, 1 by root 2, I told you this is maximum entanglement. So 1 by root 2, 1 by root 2. And then if we calculate S, we get log 2. This value doesn't matter, but it just says that like S, the more the value of S, the more entanglement there is. And the maximum there can be is S max is log 2, and that is if lambda 1 and lambda 2 are both 1 by root 2. Okay, so this is the Schmidt decomposition and corresponding von Neumann entropy. So the value of the Schmidt coefficients, that is lambda 1 and lambda 2, are more important than the actual basis we are using, because that is what it tells us whether the state is a product state or an entangled state. Okay, so if any of this was confusing, it's okay. We will not be using this Shannon entropy or the Schmidt decomposition any further. It is just to provide you an intuition to say what kind of states can there be for two qubits and how do we understand what kind of state it is. Okay, so moving on to one more topic, just touching upon this, and then I'll give you a quick break. So if you didn't understand that also, just pay attention for 5 minutes here, because this is important. This will be used again and again during the rest of the presentation. Okay, so Bell states. So Bell states are 4 maximally entangled states based on the definition we saw. They are also called EPR pairs or EPR states. EPR stands for Einstein, Podolsky, Rosen. They are 3 scientists, Einstein, of course, who wrote a paper questioning things about quantum mechanics. We'll touch upon that in Bell's inequality. And they also did some analysis and suggested some things about these states. So the 4 states are the one we saw yesterday, 0, 0 plus 1, 1 by root 2, and then 0, 0 minus 1, 1 by root 2, 0, 1 plus 1, 0 by root 2, and 0, 1 minus 1, 0 by root 2. If you look at them, all of them are maximally entangled. Like 1 by root 2 is the coefficient everywhere. Plus or minus, that doesn't matter. And yeah, these are all 4 independent states as well. They're 4 independent states, orthogonal, so you can use them as a basis. It's called the EPR basis. But these states will keep popping up again and again and again. And just the important thing to keep in mind is that if you have this state, and if we measure the first qubit, it directly decides the state of the second qubit, which is what we touched upon yesterday with entanglement. Say we take this state and we measure the first qubit. Say the first qubit turns out to be 0. Then the second qubit will have to be in the state 1. Because if we measure the first qubit 0, we know it is in this state. It cannot be in this state because the first qubit is 0. That means the second qubit has to be 1. So that is the idea of these states, that if you measure one qubit, you know the state of the other. And we will be using these in all of our algorithms. Okay, so if you don't remember the Schmidt decomposition or the Shannon entropy, it's cool. Just remember Bell states, maximally entangled, you measure one, you know the state of the other. Okay, so this is the formalism for 2 qubits. This entire thing can be generalized to n qubits, including the vector space, the dual space, the inner product, the Schmidt decomposition, the von Neumann entropy, all can be generalized to n qubits. We will not do that in this session. If you're interested, you can look into it. But the same exact ideas follow. Okay, so I will stop for a 5-minute break here. After this, the amount of linear algebra ends, like the strong linear algebra ends here. Okay, from now on, we will be defining quantum gates and we will be using them to do calculations. So we will stop for 5 minutes now. And if anyone has any questions, you can also ask. Okay, I don't see any questions, so we'll just take a few minutes break and we will resume at 11:20. Okay, if this part was not very clear, it's totally cool. Just remember what is a vector space for multiple qubits and the Bell states. Okay, there's a question. Can you give us a tangible explanation of tensor and tensor products, as in dot products deals with projections? Um, Tensors are something quite different, so we are not using them here as such. We're using vectors. So tensor products are not dot products. Okay, the dot product is like an inner product. The tensor product takes us from two vector spaces to a single vector space. The dot product and inner product takes us from two vector spaces to scalars. So there is no relation between tensor products and dot products. Dot products and inner products deal with projections. You're right there. Dot product in the real space is A dot B is just the projection of A on B or the projection of B on A. Inner product is a generalization of dot product, which you can think of the projection of one complex vector on the other. It is something like that. So in that sense, you're right, but tensor products don't relate to that. Once we've defined a new vector space using a tensor product, we can define an inner product there, and even in the new space, it behaves exactly like a vector space. So the inner product again is a projection there. In our new vector space that we've created using tensor products, in that vector space also our inner product is nothing but a projection. Okay, so I hope that answers your question. Okay, a geometric view of the tensor product. So the way we are using tensor products, I don't think there is a simple geometric view, at least I'm not aware of it. So tensor products and tensors are used in other contexts like fluids and other stuff. And in fluids, we do have like a geometric view of what a tensor can be and how it derives from vectors and how its properties come up. So if you're interested in that, maybe look into fluids. But for now, it will be too much of a deviation to go into fluids to try to explain that. It will take probably half an hour to an hour. So something maybe you can look into if you're interested. In the way we have defined it, just to create another 4x1 vector space, I can't think of a geometric view to visualize that. It's just the way of thinking of two qubits together. Okay, thanks for the questions. So I hope you had a few minutes to just take a quick refresh. And from now on, don't worry, no linear algebra if that was looking a bit complicated. From now on, we will just be doing simple operations. We'll define what are quantum gates, and then we will use them to do some calculations and some cool examples. Okay. So let's think back to what we're doing. We're trying to use quantum computing. So to use quantum computing in classical computers, what do? We first define bits. After we define bits and we have our pieces of information, we define something called classical gates. These are things that do operations on bits. For a 1-bit gate, we have the NOT gate. And for multiple bits, we have AND gate, OR gate, NOR gate, exclusively OR gate, etc. So they take bits and they do computation. And this is how we build up more complicated circuits and we do our calculations and everything in classical computing. Similar to classical gates, we have quantum gates that will perform operations on qubits. And we'll use these quantum gates to do different kinds of computations. So what are quantum gates? Quantum gates are unitary operators. So reminding you operators from our previous session, operators, the short form, the short memory for us is they are matrices that take us from one vector to another. Okay. Operators or linear maps or whatever we call them is matrices that take us from one vector to the other. And yeah, so you can think of quantum gates as unitary matrices. What are unitary matrices? Might have seen it in matrix algebra. In case you haven't, unitary matrices are those given by this definition. U conjugate transpose is equal to U conjugate transpose U is equal to I. This symbol means conjugate transpose, meaning if you have a matrix, you take its transpose and then you take the complex conjugate as well. Okay. So if this definition is new, the reason for this extra ruling on what quantum gates can be is just to maintain the normalization of a vector. So if you remember, we defined more like if psi is alpha, sorry, alpha times 0 plus beta times 1, and we said mod alpha squared plus mod beta squared is 1. The reason we said this is we want the norm of psi to be 1, inner product of psi with psi, which is nothing but this, to be 1. So now if we do an operation on psi, we take it to a different vector. We want that new vector's magnitude to also be 1. So let's say we operate some unitary operator u on psi, and we get u times psi. We want to take inner product of u times psi with itself. Basically, we want to find out the magnitude of u times psi. So then inner product of, so the dual vector of u times psi is equal to psi times u conjugate transpose. You can think of this as sort of in matrix algebra, AB the whole transpose is nothing but B transpose A transpose. That is what is happening here. That's why the dual of psi times U conjugate transpose. And so we have inner product of psi times U conjugate transpose U psi. We know this is nothing but the inner product of psi with psi. So U conjugate U transpose U is going to be I, identity. So that is the definition we gave. That is the definition we gave earlier here. So it's just unitary matrices. Basically, we want operators or quantum gates to take us from a normalized state to another normalized state. So anything that takes all vectors to other normalized vectors is an acceptable quantum operator. Okay, that's all it is. It's just matrices that will take us from valid quantum states to other valid quantum states. Anything that does that can be a quantum gate. So let's start by looking at single qubit quantum gates. So this will be the set of 2 by 2 unitary matrices. So for a single qubit, we have 2 by 1 column vectors. So our matrices will be 2 by 2. So we will look at a few gates which we might use and are otherwise very commonly used in quantum computing. And we'll just try to understand them. Okay. So the first of those gates is the NOT gate. The NOT gate is given by this definition 0110. Like the name suggests, like its classical equivalent, it is a gate that takes the 0 state to 1 state. And it takes the 1 state to the 0 state. Basically the NOT operation. Okay. So if we operate this on some general state like this, it just flips the coefficients because it takes 0 to 1 and 1 to 0. We get beta times 0 plus alpha times 1. So that is the NOT gate, just a quantum version of the classical NOT gate. Why on earth would we name this gate X when it's the NOT gate? It's not just physicists having some arbitrary naming methodology. Their naming methodology is arbitrary a lot of times, but here they have a reason. The reason is this can be visualized as a rotation of 180 degrees about the x-axis on the Bloch sphere. So if you remember that cool Bloch sphere that we talked about for visualizing a single qubit, so what we are doing, if we take a state and we rotate it 180 degrees about the x-axis, we get a new state. You can think about it. Our zero state is here. If we rotate 180 degrees above the x-axis, we end up at 1. Similarly, if we rotate 180 degrees above the x-axis, we end up at 0. That is what happens for all states. Okay, so that is why it's called the x gate. We're just rotating the state 180 degrees above the x-axis. So this is the NOT gate. It takes 0 to 1, it takes 1 to 0, and it takes a general state alpha 0 beta 1 to beta 0 alpha 1. Okay, this is the NOT gate. We'll use the X notation for this. The next important gate is the Z gate. So the Z gate takes 0 to 0, does not affect 0. It takes 1 to minus 1. So if we take a general state alpha 0 plus beta 1, it takes it to alpha 0 minus beta 1. Because it takes 0 to 0, it takes 1 to minus 1. This is what happens to a general state. And this is equivalent to a rotation of 180 degrees above the z-axis. Hence the name Z-gate. I'm not doing the visualization for all gates. You can just try it and you will see that it works out. The way to do the visualization, just think about what this rotation does to theta and phi, and then see how the basis vectors change when you change theta and phi correspondingly, how 0, 1 changes, and you will see that what is happening is what is mentioned here. Okay, it's not important for us, just know the gates. That's more important. This is just to give a side hint as to how it relates to spin half systems. So what is our Z gate? It takes 0 to 0, it takes 1 to minus 1. So it takes alpha 0 plus beta 1 to alpha 0 minus beta 1. This is our Z gate. Then our third gate is, you guessed it, the Y gate. We will not be using this gate that much, but it is similarly a rotation of 180 degrees about the Y axis. It takes the 0 state to I times 1, and it takes the 1 state to minus I times 0. It takes alpha 0 plus beta 1 to minus I times beta 0 minus alpha 1. The reason I take the minus I outside is, remember, for a single qubit, this global phase does not matter. So it's what is inside that matters. So what is inside is just a 180 degree rotation about the y-axis of the original vector. So if you look at the Y gate, you can sort of think of it as a combination of the effects of the X and Z gate. We switched alpha beta and we also changed the sign of the second, the coefficient of 1. So we are sort of doing both at the same time, while adding a global phase as well. Okay, so these three matrices, the X, Y, and Z matrices, just a small tangent from quantum computing, are called the Pauli matrices. So this Pauli matrices is something you will see all over QM and linear algebra, like everywhere. It is super commonly used. It's very useful. They have a lot of very, very cool properties. We won't be going into them, but if you want to look into it later, I'd suggest you do it. It's pretty cool. And there's a reason why these gates are the rotation. If you think about it, and yeah, so these gates will not change the corresponding vectors that have definite spin in those directions. So if you think of the X gate, it does not change the X plus comma X minus states. It just adds a global phase. It doesn't do anything else to these two. If you think of the Z gate, it does not change the 0 and 1, just adds a global phase. To 1, it adds a global phase of minus 1. If you think of the Y gate, it will not change the Y plus and Y minus states, just add a global phase. I'm not proving this, just mentioning this because, and the reason is, well, these are the matrices that correspond to rotation in those directions. So if you think of it, if you already have a spin in the Z direction and you're rotating about the Z axis, it will naturally not affect that spin. Similarly, if you already have your spin in the Y direction and you're rotating about the Y axis, it does not affect that spin. This is how it again relates to spin half systems. So that's why the Pauli matrices is something you'll see a lot used in spin and angular momentum. Small tangent, does not impact the rest of our session. For us, all that matters, X gate, NOT gate, Z gate, another gate that does this, Y gate does this. We won't use the Y gate again. And we'll use the X and Z though. And one more cool gate that we will be using a lot. It is called the Hadamard gate. So the Hadamard gate is this matrix. And what it does is it takes 0 to 0 plus 1 by root 2. And it takes 1 to 0 minus 1 by root 2. So it is taking 0, 1 to x plus and x minus. So we take a general vector alpha 0 plus beta 1. It takes it to alpha plus beta by root 2 times 0 and alpha minus beta by root 2 times 1. I'm skipping steps of algebra. Like you can actually multiply this matrix with this and see that this is what happens. But yeah, this is what it does. Sometimes it is probably one of the most, it is the most commonly used single qubit gate in quantum computing, this Hadamard gate. Some people will call it the square root of NOT gate. The reason they do that is because, say, the 0 state is on the top of the block sphere, the 1 state is at the bottom, and it takes it to 0 plus 1 by root 2, which is like halfway through the NOT gate, and it takes 1 to 0 minus 1 by root 2, which is like a halfway rotation to 0. So it is doing half the rotation of a NOT gate, but this naming is stupid and don't follow it, because if you think of that, then you might think applying the Hadamard gate twice will take us to a NOT gate. No, Hadamard gate twice H square is the identity matrix. You can take H square and check. So if you see this naming notation, remember that is not the case. All you need to know about the Hadamard gate, it takes 0 to 0 plus 1 by root 2. It takes 1 to 0 minus 1 by root 2. Okay. So this is the Hadamard gate. We will see this gate again, and we will see it is pretty useful. So just to summarize single qubit gates, what we need to remember for future, for the rest of the session: X gate, NOT gate, 0 to 1, 1 to 0. Z gate, 0 to 0, 1 to minus 1. Y gate we will not use again. Hadamard gate, 0 to 0 plus 1 by root 2 and 1 to 0 minus 1 by root 2. That's all we need. Okay. And now we go to multiple qubit gates. So again, a general statement on multiple composite quantum systems. The operator space for them is the space of tensor product of the operators of the individual systems. So if we have operators for individual vector spaces, we take the tensor product, and that's what gives us our new operator space. And so if you are not interested in the general system, for us, instead of 2 by 2 matrices, we will have 4 by 4 matrices. Our vectors are 4 by 1 column vectors now. So our general, all our operators will be 4 by 4 matrices for 2 qubits. So the set of all possible quantum gates is all of the unitary 4 by 4 matrices. Why unitary? Because we want them to keep the normalization same as earlier. We will visualize and use them in two ways. Sometimes we will write this operator as a 4 by 4 matrix like this. We will just write down the matrix and say, this is what it does. If we have a vector like this V, we will just do U into V. That is, we'll just multiply the matrix and the vector, and this will give us a new vector. Okay. So matrix, vector, new vector. So this is one way we can use 2 qubit quantum gates. The second approach which we will use is useful when we are actually operating on only 1 qubit, but we are thinking of the 2 qubits together. So this is also one way we can define an operator. So what this means is I tensor product X. I is the identity matrix. It means we're operating identity on the first qubit and we're operating the X gate on the second qubit. Operating identity means we're doing nothing to the first qubit. We're just operating on the second qubit. So in that case, we don't want to sit and compute our vectors as a 4 by 1 column, and we don't want to sit and compute our 4 by 4 matrix. We just leave them as this, and then we will operate on vector also. We will write in this form. Take this example vector 0 plus 1 by root 2 tensor product 0. And when we operate W on R, just operate the first operator I on the first vector, operate the second operator on the second vector. That's it. And then take tensor product of the whole thing. Okay. So we operated the first operator on the first thing, and the second operator on the second thing, and then take the tensor product after the operations. So I on this does not do anything. X is the NOT gate on 0, takes it to 1. So our final state is just 0 plus 1 by root 2 tensor product 1. And we can just leave it like that. So only when we have gates that impact like both qubits at the same time, we will write them as a 4 by 4 matrix. And we will write the vector as a 4 by 1 column vector and operate. If we have operators that are just going to impact one qubit, we will write them like this in this tensor product form, and we'll operate them on the individual qubits and keep them as individual qubits since we're more comfortable like that. Okay. So we are just going to look at one important 2-qubit quantum gate. This is the controlled NOT gate. C naught is nothing but the controlled NOT gate. So like the name suggests, what it does, if it operates on 2 qubits, if the first qubit is 1, then it performs the NOT operation on the second qubit. If the first qubit is 0, it just leaves the second qubit untouched. So controlled NOT gate, depending on the value of the first qubit, it either performs NOT on the second qubit or does nothing. So that's why 0, 0, the first qubit is 0, so it does not change the second qubit, so it remains 0, 0. 0, 1, first qubit is 0, does not affect the second qubit, so it remains 0, 1. 1, 0, first qubit is 1, second qubit is 0, first qubit is 1, so it changes the second qubit. So the new state is 1, 1. 1, 1, similarly the first qubit is 1, so the second qubit is operated with a NOT, so it becomes 1, 0. So this is all the control NOT gate is. It is a very useful gate, and it is the gate that we use to create entanglement. So just to summarize the control NOT gate, if the first qubit is 0, second qubit is not touched. You get the same state. If the first qubit is 1, you flip the second qubit. You operate a NOT on the second qubit. And that's it. That is the control NOT gate. That is all the gates we will be using today. And just touching upon measurement, we already did a lot on measurement in the previous session. We can make a measurement on any orthonormal basis. What does that mean? Something like 0, 1, something like x plus comma x minus. For 2-qubit systems, an acceptable orthonormal basis is this, like all the 4 possible states, like qubit 1 and 0, qubit 2 and 0, and like all 4 corresponding states. And when we make a measurement on an orthonormal basis, it will decompose into one of those basis states. So our vector will become either 0 or will become 1 with a given probability. It will either become 0 plus 1 by root 2 or 0 minus 1 by root 2, the given probability. Similarly, for multiple qubits, it will either become 0, 0 or 0, 1 or 1, 0 or 1, 1 with a given probability. So when we are talking about quantum mechanics, we were very cool with probabilities. When we're talking about quantum computing, we want to actually make some calculation. So we don't really want to make a calculation with a probability. I don't want to tell you the answer is 25 with the probability 60% and the answer is 15 with the probability 40%. So most likely we will make this such that we know what the answer is based on a measurement. But then initially we saw that a qubit can be in any superposition of 0 and 1. So naively we might think a bit can have any one of 2 states, but a qubit can have like infinite states. If you think of alpha and beta, they are continuous numbers. So we have infinite states. So we can store infinite information in a single qubit. So we don't need many qubits to do computation. That is not entirely true, because we can only, when we make a measurement, we can only make a measurement on the basis of 2 states. So we can do some special things that we can't do in classical computing, but it's not like 1 qubit. We can actually make a measurement on an infinite basis. When we make the measurement, we can only get this much information. So we have to be clever in how we do our calculations, but there's a limit. That's what this measurement says. And you might think, okay, I have a solution for that. Let's just take this qubit and make like infinite copies of these qubits. And if we make these infinite copies of this qubit and we make a measurement on all of them, we can actually back calculate the probabilities. And so using the probabilities, we can back calculate the exact states. So aren't we making a measurement on an infinite basis? That's a very valid argument. And the answer nature has is no, you can't do that. Because there is something called a no cloning theorem in quantum computing. So what does that mean? No cloning, like the name suggests, we cannot make an exact copy of a qubit. This might sound very weird, as we can easily copy the state of a classical bit. But in quantum computing, we cannot make a copy of a qubit. So since we cannot make a copy of a qubit, and each qubit we can only measure once, and what the measurement is only in an orthonormal basis, this is sort of the limit of using, even though we have infinite states we can access, this is the limit of using qubits in quantum computing, and why we can't just magically use all infinite states and make all computations in like one qubit. So that ends our discussion on quantum gates and quantum measurement. And now we will use whatever we learned in the last half an hour and initially and everything to look at some examples. So these are all examples where either classical computers cannot do this or quantum computers can do things better than classical computers. I will just remind you that these are very few and very particular examples. It is not that quantum computing is just outright superior to classical computing and quantum computing is just going to wipe classical computing out of the floor. No such claims. There are certain niche fields where we have theoretical evidence to show that quantum computing can do something that classical computers cannot. So we are going to be looking at these niche examples because, of course, we want to be interested in quantum computing. So we'll look at these particular cases where quantum computers can outperform classical computers. So for all of these examples and in general in quantum mechanics and quantum computing, you will keep seeing two characters or names, Alice and Bob. So all examples, we have these two, Alice and Bob, and they will be our guinea pigs for all our experiments, all our stories, all our thought process. Okay. So the first example, so Alice and Bob are on a mission, and Bob wants to send Alice 2 bits of classical information. So, but Bob is not able to send Alice more than 1 bit. If he could send 2 bits, job done. He wants to send 2 bits of classical information. But Bob also has the option to send 1 qubit. Can he send 2 bits of information using just 1 qubit? The answer is yes. He can do this if Alice and Bob prepare beforehand with some planning. Okay. So what is the preparation for this? Alice and Bob create 2 qubits in a Bell state. So the Bell state is psi equal to 0, 0 plus 1, 1 by root 2, a maximally entangled state. And they create some sort of a code that will tell Alice what is the information based on the measurement that she can make. Okay, this is she, not he, typo. What is this code? I will tell you in a bit. But what Alice and Bob prepared, they prepared a secret code that tells Alice, okay, if she makes this measurement, what will happen, what she will get, and Bob and Alice have this 2 qubits in a Bell state, and they both take one of these qubits. So now Bob wants to send the information. Now Bob has got, okay, this is the information I have to send. He knows whether he has to send 0, 0 or 0, 1 or 1, 0 or 1, 1. Remember, 2 bits of information. So Bob has to either tell Alice the secret code is 0, 0 or 0, 1 or 1, 0 or 1, 1. Alice has 1 qubit of the two end of the Bell state. Bob has the other. So Bob takes his qubit, and if the information to be sent is 0, 0, he does nothing to the qubit. If Bob wants to send the information 0, 1, he operates the Z gate on his qubit. So operating Z on 0, 0 plus 1, 1 by root 2. When I say Z, this is actually Z tensor product I. I am operating Z only on 1 qubit. So it does not affect 0 and it changes the sign of 1. So that's why you get 0, 0 minus 1, 1 by root 2. So similarly, if Bob wants to send the information 1, 0, he operates the X on his qubit, the qubit he has. So X is the NOT gate, and so 0, 0 gets transformed to 1, 0. 0 gets transformed to 1, and 1, 1 gets transformed to 0, 1 because the not applies on the first qubit. So you get this state 1, 0 plus 0, 1 by root 2. That's the combined state of the two qubits now. If Bob wants to send the information 1, 1, he operates both Z and X. So operating Z will change to this state, and then applying an X to that will also exchange the qubits, leading to this final state 1, 0 minus 0, 1 by root 2. If you look at the first qubit, it has both changed sign, changed qubit. It was 0, 0, now it's 1, 0, and similarly 1, 1 has become 0, 1. And there's a change of sign in the second term because you are operating the Z gate as well. So now, depending on whether we want to send 0, 0, 0, 1, 1, 0, or 1, 1, our two qubits are in one of 4 different states. Now, all Bob has to do is send his qubit to Alice. And now Alice has both qubits in hand. She can perform a measurement on this 4 qubit basis. So we have 0, 0 plus 1, 1 by root 2, 0, 0 minus 1, 1 by root 2, 1, 0 plus 1, 0, 1 by root 2, 1, 0 minus 0, 1 by root 2. So these are 4 orthonormal states. Alice will just measure the 2 qubits to see which state it is. And depending on which state, she knows which is the secret code that Bob wanted to send her. So with some preparation beforehand, with just 1 qubit, we have sent 2 bits of information. And yeah, that is pretty cool. Think of this. You cannot have sent this information using even any predefined code by sending a single bit. Not possible. But it is possible by just sending 1 qubit if you've done this preparation beforehand. So that is called super dense coding. Why it's called super dense coding? Because you're doing the coding of the work of 2 bits using just 1 qubit. So that is one example of showing why quantum computing is cool. So now a second example with a lot cooler of a name is quantum teleportation. So quantum teleportation, first let's look at the problem statement. So now Alice and Bob are on a mission. Bob goes to a secret hideout where he has to enter a specific qubit state as an access key to finish the mission. So there is this secret hideout, and there is there's some vault in that hideout. The only way to access that vault is to enter a particular qubit state that only the company knows. Bob can carry 1 qubit with him, and he can modify that qubit to any state, but then he cannot get the information of what that state is. He does not get access to that state, neither does Alice, until Bob has already entered the hideout. So Bob has gone into this hideout. He has some normal qubit in a known state, say 0 or 1. He knows what state it is, but he has no idea what the access state is. Alice, after Bob has already entered the qubit in a known state, Alice can get access to this access key qubit, but she can only transmit to Bob 2 bits of classical information. Say she can get the lights to flicker in a particular way, or some way she is able to transmit to Bob 2 bits of classical information. And with these 2 bits of classical information, can she transfer this entire qubit state to him? Remember, the access qubit is with Alice. She has to teleport this qubit state to Bob for him to complete. So can she do this? If you think of it classically, then it does not, like not classically. If you just think about it, there are some issues here. Firstly, just give me 1 second. I'm sorry. Yeah. So firstly, Alice gets access to the qubit. Even if she does, she cannot find out what that state is exactly. Say it is some 1 by root 3 times 0 plus 2 by root 3 times, or root 2 by root 3 times 1. It can be one of infinite states. She cannot find out because she can only make one measurement. And if she makes that measurement, it only gives her a probability of what it could be. It's not like that state access key has to be in 0 or 1. So with one measurement, she cannot find out what the qubit is. She only has access to this access state qubit. And even if she were able to, think of it with something like 1 by root 3 and root 2 by root 3. it would take infinite bits to transfer this information. She cannot do it with 2 bits. How will you inform like some a set of like rational numbers, real numbers, not integers or anything like that, with just 2 bits? You can't. But with quantum computing, you can actually teleport the state if you have some preparation like we did in the beforehand. So again, we will use these Bell states. Bell states are awesome. We can use them to do all sorts of cool stuff. So Alice and Bob create a set of qubits in a Bell state, and Bob takes one of these 2 Bell state qubits with him. And again, they've planned a code for what Bob should do to his qubit depending on the 2 bits of classical information he receives. Okay. And now we will look at a circuit of things that Alice does and then Bob should do, with which we can teleport this access key qubit to Bob. Even though we can't measure it, even if we measure it, we cannot transfer that information with a finite number of bits, we can still teleport this access qubit to Bob. Okay. So let's look at quantum teleportation. So this is the circuit. Don't worry, I'll explain step by step what is happening. So this time we are working with a 3-qubit system. Our 3-qubit system psi 0 is psi. This is the access qubit. And which is some general state, alpha 0 plus beta 1. Okay. We don't know what the state is. Alice just has access to this. And beta 0 0 is the Bell state. 0 0 plus 1 by root 2. So one of these 2 qubits, say qubit 1 is the access and qubit 2 is the first qubit of the Bell state. These 2 are with Alice. Qubit 3 is with Bob. So Alice can only operate on qubit 1 and 2. Bob can operate on qubit 3. Okay. Right now, qubit 2 and 3 are in the entangled Bell state, and qubit 1 is just separate the access key. Okay. So now what is step 1? Step 1, Alice applies a C0 gate on her 2 qubits. So that is the first qubit of the Bell state and the general qubit. So what is the controlled NOT gate? If the first qubit is 0, then it does nothing to the second qubit. If the first qubit is 1, it applies a NOT gate on the second qubit. So let us see what happens. So now we are looking at alpha times 0. So the first qubit is 0. So the second qubit remains the same. So we have the same state. So alpha 0 just splits like this. Now the second part where the first qubit is 1, we flip the second qubit. So now our new state is 0 1 plus 1 0 by root 2. So this 0 0 became 1 0 and this 1 1 became 0 1. When the first qubit is 1. So this is our psi 1. This is our new state of the 3 qubits. We have alpha times 0 times 0 0 plus 1 1 by root 2 plus beta times 1 times 0 1 plus 1 0 by root 2. So this control NOT gate has now created some entanglement between the access qubit and the first of the 2 Bell state qubits. It has created some link between them. And now we have this new state psi 1. Now step 2, we apply a Hadamard gate to the access qubit. So what is the Hadamard gate? Hadamard gate takes 0 to 0 plus 1 by root 2 and it takes 1 to 0 minus 1 by root 2. So this is the Hadamard gate and we are applying it on the access qubit. So alpha times 0 goes to alpha times 0 plus 1 by root 2. Beta times 1 goes to beta times 0 minus 1 by root 2. The 2 qubits of the qubit 2 and qubit 3 remain completely unchanged through this. Okay. So now we have the psi 2 and we can rewrite psi 2 in this form. So what we want to do is we want to separate out Alice's and Bob's qubits and see what the state are. So if you take this 0 0 0, it is 0 0 times 0 as well. Like this is the combined state that I'm talking about with these two. I'm writing this as 0 0 and 0. So similarly, I have this state. This is 0 0 1. So I'm writing this as 0 0 and 1. So then I'm bringing these two states into the same bracket and I'm writing, and I got this 0 0 times alpha 0 plus beta times 1. I am doing the exact same thing with all of these states. There's totally 2 into 2, 4, and 2 into 2, 4, 8 states. So those 8 states is what we are splitting into 4 different brackets of 2 each. So 4 into 2, 8 states. So if we do that algebra, we get this. And what are we getting? So if we look at Alice's 2 qubits, they are either 0, 0, 0, 1, 1, 0, or 1, 1 now. And this is a standard 2 qubit basis. And Alice can make a measurement. And once she makes a measurement, she knows what that measurement is. It decomposes Bob's state to one of these 4 different states. Either it gives us, if the measurement is 0, 0, Bob's qubit is now the access qubit. If the measurement is 0, 1, Bob's qubit is a modified version of the access qubit. And so on and so forth. Like depending on which measurement it is a modified version of the access qubit. Bob's qubit is now. So now, once she has made this measurement, all she has to do is tell Bob what she got. If she got 0, 0, we saw that Bob's qubit is nothing but the access qubit. He has to do nothing. Similarly, if she got 0, 1, Bob's qubit is this. And if he does an X, which is a NOT gate, he gets the access qubit. 2X leads to this. If her measurement is 1, 0, Bob has to just do Z to this. It flips the sign of the second one, and we get the access qubit. If the state is 1, 1, Bob has to do both X and Z, and this qubit also transforms to the access qubit. So all Alice has to do is transmit 2 bits of classical information, which is this. Is it 0, 0, 0, 1, 1, 0, or 1, 1? What is the result of her measurement? And based on that, Bob will do either nothing or X or Z or both XZ. Yeah, Bob applies the required gates, and he now has the access key qubit, alpha 0 plus beta times 1. This is the state of Bob's qubit. And we have actually managed to teleport this access qubit from Alice to Bob. Think of it. We cannot, if we measure this qubit, we destroy the qubit, and we cannot, even if we could measure, we cannot transmit this with even an infinite number of bits of, we need infinite bits of classical information to transmit the information. But with just 2 bits of classical information, we have managed to teleport this qubit from Alice to Bob, and Bob can complete his mission. We might think of a couple of paradoxes here, but just to clarify, there are no paradoxes. Firstly, we might think this access qubit has gone from Alice to Bob in faster than speed of light, but that is not the case. Remember, Alice had to transmit 2 bits of classical information, and the transmission of the classical information is less than the speed of light. So the total transmission of information is less than the speed of light. It does not break that rule of relativity. That rule of relativity holds. Secondly, we said there's a no cloning theorem, but we supposedly made a clone of the qubit. The answer is we didn't make a clone. We destroyed the original qubit to teleport it to the new space. So we still had only 1 qubit that we can make that measurement on. We did not make a copy of it. So we did not go against the no cloning theorem as well. But without doing either, we have managed to teleport a qubit from Alice to Bob, and that is quantum teleportation. So again, I will take a 5-minute break here. After this, we will do one more example of a computational process that quantum computers can do faster, and then we will touch upon, this will take a bit of time. Then we will just touch upon how to build a quantum computer, and we will end with Bell's inequality. Okay, so I will again take a 5-minute break and answer any questions that anybody might have. Okay, there's a comment. Don't they generate SU2 groups as well? I'm guessing this is in relation to Pauli matrices, and yeah, Pauli matrices, yes. They're used in Lie algebra and a lot of math. Okay, the implications of the no cloning theorem. So suppose we had some qubit in some state alpha 0 plus beta 1, and we could make infinite clones of the state. Then we can make infinite measurements on this qubit, and we can back calculate the probabilities and calculate alpha and beta. So in theory, we can make a measurement on more than an orthonormal basis. We can make a measurement on an infinite basis almost. So that means we can do so much with the infinite states of a qubit. The no cloning theorem protects from that and says you cannot make a copy, so you can only make one measurement on a qubit, so you cannot find out its exact state, alpha 0 plus beta 1, unless you make like a perfect orthonormal measurement and you know the states beforehand. For example, you know the qubit is only going to be in 0 or 1, then you can make a measurement on the 0 and 1 basis and find out the qubit. But if you only knew the qubit is some alpha 0 beta 1, you have no idea on it, you cannot find out it exactly. You can only make a measurement on 0 1 or 0 plus 1 by root 2, 0 minus 1 by root 2. So it sort of tells us the limitations of, even though we have infinite states to use, we are limited in what we can find out about the qubit, and so we are limited in what we can do in quantum computing. It's not like we can use those infinite states like infinite memory and operate on all of them and measure from all of them. So that is the implication of the no cloning theorem. Okay, so I hope everyone had a quick break. Let's resume. This will be the last 50 minutes to maximum of an hour of the session. I'll make sure to wrap up by 1. And yeah, so we saw, I hope I'm audible and the screen is visible, just confirming.
Yeah, it's fine.
Okay, cool. So we saw two examples at the end there: super dense coding and quantum teleportation. So what we saw was that with super dense coding, you can send 2 bits of classical information with just 1 qubit, and sort of a ulta of that, the reverse of that is what we saw with quantum teleportation, that you can transport or teleport 1 qubit with just 2 classical bits of information. So two cool examples with Alice and Bob. And now we are going to look at something called Deutsch algorithm. So this is a particular computational task. This is something that is some like a computer would be asked to do in certain time. So the same task can be done faster by a quantum computer. So let's look at the problem statement. And if you ever read like quantum supremacy in any of the news articles, it's typically something like this is what they mean, where they have a certain computational task and a quantum computer can do it faster than any classical computer on the earth can. So that is what they mean when they say quantum supremacy. Let's look at one example where in theory at least a quantum computer can do faster than a classical computer. So the problem that we are working with is, say we have a function f of x that operates on one bit to give another. So we go from, so our f operates on 0 and it gives either 0 or 1. It operates on 1, it either gives 0 or 1. So it takes 1 bit to another 1 bit. Okay. And we want to find out f of 0 plus f of 1 mod 2. This is called the exclusively OR gate in classical computing. So we want to find out f of 0 exclusively OR f of 1. What this means is, if f of 0 is equal to f of 1, that means the result of this is 0. If f of 0 not equal to f of 1, then the result of this gate is 1. Yeah. So f of 0 is equal to f of 1, we get 0. F of 0 is not equal to f of 1, we get 1. Okay, that is the exclusively OR gate. And we want to calculate this using classical or quantum computing. In classical computing, how can we do this? We will have to operate f on 0, we'll have to operate f on 1, and then we can take the exclusively OR and check whether it's going to be this thing. F of 0 is going to be equal f of 1 or f of 0 is not going to be equal to f of 1. We will have to use f 2 times. And for all of our examples, these functions are the complicated ones. So this is the one that will take the longest time. So you have to operate f 2 times. It could be some very complicated function for all we know. So this takes a while. So what we're going to show is, in quantum computing, we need to operate f only one time, and that is enough for us to find f of 0 exclusively or f of 1 by operating just once. Again, this is the circuit. Don't worry about the symbols. I will explain step by step what is happening. Okay. So step 1, this time we're starting with 2 qubits in the states 0 and 1. So the first qubit is in state 0, second qubit is in state 1. Then we are applying Hadamard gates on both of them. So that is why I've written Hadamard, tensor product Hadamard. What I mean is, I'm applying a Hadamard gate on the first qubit, a Hadamard gate on the second qubit. So it takes 0 to 0 plus 1 by root 2 and 1 to 0 minus 1 by root 2. Okay. So now we have our 2 qubits in this state. This is still a product state. There's no entanglement or anything. The first qubit is in this state. The second qubit is in this state. Now we apply a special gate that takes these 2 qubits. Say this is qubit x and this is qubit y, to x comma y plus f of x. How it does this? Think of it as a black box for now. I'm not explaining the gate, but you can check it is a unitary operation, and therefore it is an acceptable quantum gate. How exactly we design this quantum gate and all is not relevant, but what it does is it takes x comma y to x comma y plus f of x. Again, when I say y plus f of x, if y is 1 and f of x is 1, it becomes 0. So this is an exclusively OR operation. So this is the only time we are operating f. So only once we are going to operate it on the on the xy qubit set, and we're going to operate it on x, and we're going to add exclusively or add that to y. So we are using our one operation of f on x qubit, and we have a gate that adds this f of x exclusively or to y. Okay. So what does this mean really? If f of x is 0, comma y is 0, then the result of f of x exclusively or y is 0. If f of x is 1 and y is 1, also it's 0. If f of x is 0 and y is 1, we get 1. If f of x is 1, y is 0, we also get 1. Okay. So let us look at what happens to the states when we operate this special gate. So let's take the first case that f of 0 is equal to f of 1. So if f of 0 is equal to f of 1, now this is our initial state. This is the state we are going to operate this gate on. So if f of 0 is equal to f of 1, then whatever happens to this qubit is going to be the same whether the first qubit is 0 or 1. So what we want to do is we want to find psi2. We will find what is going to happen in 0 times 0 minus 1 by root 2 plus 1 times 0 minus 1 by root 2. So if f of 0 is f of 1, since we are going to exclusively add f of x, whatever we are adding here is the same thing we are going to be adding here. So it is just going to be 0 plus 1 by root 2 times whatever happens here. And let's see what happens here. If f of 0 is equal to f of 1 is equal to 0, then exclusively OR does nothing. Then 0 will remain 0 and 1 will remain 1. So 0 minus 1 by root 2 will remain 0 minus 1 by root 2. But if f of 0 is equal to f of 1 is equal to 1, then 0 becomes 1 and 1 becomes 0. 0 becomes 1 and 1 becomes 0. And that what that means is 0 minus 1 by root 2 becomes minus of 0 minus 1 by root 2. It becomes 1 minus 0 by root 2. So that is why our end result is plus or minus the same state, depending on whether f of 0 equal to f of 1 is equal to 0 or 1. But regardless, we can see the states of the two qubits. This global phase will not matter. Okay. What happens if f of 0 is not equal to f of 1? So if f of 0 is not equal to f of 1, let's say f of 0 is 0 and f of 1 is 1, then we get 0 times 0 minus 1 by root 2. Nothing changes here. Plus, however, when there is a 1, we will get 1 minus, let me correct myself. We will get 1 minus 0 by root 2. Because there's a 1 outside, these two flip. So when I write this together, it becomes 0 minus 1 by root 2 times 0 minus 1 by root 2. Because we got when 0, the second bracket does not change. For 1, the second bracket flips sign. So when I bring these two together, I take the minus sign outside and I get 0 minus 1 by root 2 times 0 minus 1 by root 2. And if f of 0 was equal to 1 and f of 1 is equal to 0, we'll just get a minus sign outside. You can do the algebra and check. I'm skipping a couple of steps of algebra So if you're unsure, just look through the slides and do the algebra yourself. You'll see that whatever steps I'm doing, it follows naturally. All I'm doing is just the simple like addition and like exclusively or. That's all I'm doing. But the side 2 we get now is different. Namely, if we compare the two cases, we can see the second qubit is the same, but the first qubit here is 0 plus 1 by root 2, and here is 0 minus 1 by root 2. So now we apply a Hadamard gate on the first qubit. So if f of 0 was f of 1, we had 0 plus 1 by root 2, and this guy goes to 0. So applying a Hadamard gate takes this to 0. You can check the calculation. This is what we'll get. And case 2, if f of 0 is not equal to f of 1, it takes the 0. Now we have the 0 minus 1 by root 2, and Hadamard gate takes that to 1. Okay. So now we measure the first qubit on the standard basis. If the qubit is 0, then that means f of 0 is equal to f of 1. If the qubit is 1, then it means f of 0 is not equal to f of 1. So the result is nothing but f of 0 exclusively or f of 1. That is, if it's true, the qubit is 1. If it's not true, the qubit is 0. So with that, with just one operation of f, we are able to find out f of 0 exclusively or f of 1. This would take two operations classically. And we did it by operating f only once on one qubit. So the way why this works is this idea of quantum parallelism. That is, we can operate f or any function on multiple qubit states at the same time. Even though when we measure, we have to measure into a single orthonormal basis, we can operate on like multiple single classical bits. Like we operated f on 0 plus 1 by root 2. So we managed to operate it on both 0 and 1. That's called quantum parallelism. And this allows us to find out things like f of 0 plus f of 1 exclusively or f of 1 with just one operation of f. And that is really the power of quantum computing. So you might think, okay, instead of two operations, you're using one. Big deal. But this Deutsch algorithm that I've explained is a simplified version of the Deutsch-Zosa algorithm. This is a generalization of the Deutsch algorithm or Deutsch problem. And suppose we have 2 power n bits. And we need to find out if a function on these 2 power n bits is constant or balanced. So what is a constant function? Constant function, like its name suggests, is it operates on all states and gives the same value. Balanced means it gives 0 for half the inputs and 1 for the other half of the inputs. So classically, to find out whether an operator is balanced or constant, we could require up to 2 power n by 2 plus 1 operations. Because for the first 2 power n operations, the 2 power n by 2 operations, even if we got all of them as 0, it could be that all of the remaining operations could lead to 1. So we need one more to confirm whether all of them are 0 or whether the last one is 1 and it's a balanced function. So we could require 2 power n by 2 plus 1 operations classically of f to find out whether the function is constant or balanced. In quantum computing, we require only one operation of f. And this is a generalized version of the Deutsch algorithm. We're now going to go into the step by step. Exact same ideas apply. And we can find out the value of, we can find out if the function is constant or balanced with just one operation instead of 2 power n by 2 plus 1. So n could be anywhere like 100 for all we can. A normal function could operate on 100 bits. A normal function could operate on a kilobyte of data, which is what, 8,000 bits. So you can think of the number of operations we need classically to find this out versus we only need one operation quantum mechanically. So that's why in certain niche fields like this, and this is a useful problem. We would want to know if function is constant or balanced. It could be a useful problem for a lot of things. And for that, quantum computing, in theory, can outperform any classical computer. So that is the examples that I wanted to cover. And we will now quickly touch upon how to build a quantum computer. So fundamentally, you can see that the quantum computing theory is solid. In that, we can definitively say that quantum computers can be better than classical computers in certain aspects. They can do certain things that classical computers cannot. The only question of whether quantum computers will be found in every house in the future is whether we can build a quantum computer, and how hard it is, how expensive it is, and all of that stuff. So this is the area of like primary research all over the world. A lot of companies, a lot of universities, everyone are putting in a lot of funding to try to build physical quantum computers. It is a lot more challenging than trying to build classical computers for several reasons. We will touch upon some of them. So what are some of the requirements we need to build a quantum computer? This is sometimes called the DiVincenzo criteria, after one of the scientists who proposed this criteria. So he talks about 5 points. The first is we need a 2-level quantum system where you can achieve any superposition. The second is we need to be able to couple many such qubits. The third is we need to be able to these quantum states should be stable so we can store this information at least for a small time. Fourth is we need to be able to perform operations on all the qubits, including coupled qubits, and we need to be able to define general gates. The fifth is we need to be able to measure output in any orthonormal basis we want. So we saw that all of this is what we used. We used a qubit, we needed to couple qubits, and then we needed to store this information, then perform some operations, store it again, and measure when required. For doing quantum computing, we saw that we needed all these 5 points. So let's just touch upon these 5 points with a bit more detail. It will still be brief, don't worry. And this is more a field that you can explore out of interest. And each of this is a subfield. Like if you look at superconducting quantum computing, it's a subfield. Photonic quantum computing, it's a subfield. So we'll just touch upon briefly what these requirements are and also like hint at some of the examples of quantum computing. So the first requirement is a 2-level quantum system. We cannot use something with infinite states. Like if you take a free electron and think of its position, it can be one of infinite possibilities. So that's not a qubit for us. A qubit, we need 2 clear quantum states and a superposition of those states. So one way to choose systems with only 2 states. One example is a spin-half system. People are trying to build quantum computers with electron spins as well as nucleus spins. When I say they're building quantum computers with this, I mean the thing is the qubit. So an electron spin is the qubit, or a nucleus spin is the qubit. Similar to electrons, even nucleus and other particles have spins. So this is one way. This has some drawbacks. So another possible way is to choose a system with a finite number of states, where these states all have different energies, and we make all of the states other than the ground state and the first excited state, we make all of these other states have very high energy. So typically you might have heard that states and particles settle in the lowest energy states. So that's the idea we're using here. And one example of this is quantum harmonic oscillator type systems. I'm guessing this is completely new to everybody unless you've done a quantum mechanics course. So I'll just touch upon this. If you don't understand, don't worry. So classically, we have our harmonic oscillator and we have like a frequency that defines the harmonic oscillator. Omega is equal to root of k by m, if I remember right, something like that. So quantum mechanically, the states of a harmonic oscillator are discrete, meaning you have a state with 0 energy, like a ground state, then the next excited state has like 1 exact quanta of energy more, a second excited state has 2 quantas of energy more, third excited state 3 quantas of energy more, and so on. So you can only have certain fixed energies. Classically, it is a continuous spread. Quantum mechanically, it's fixed energies. Take all this for granted. This derivation itself is another 2-hour session on quantum physics. So only reason I'm mentioning this is, so this would not be ideal for us, because the second state, for an electron to go from the first state to a second state is very possible. But if we can create something called an unharmonic oscillator, where the energy gap between the second state and the first state is large, like very large compared to the energy gap between 0 and 1, we can control and keep the electron or the particle within the ground, like the 0 and the first state. And therefore, we only have 2 states, and therefore we can control and make this a qubit. So in a lot of different areas, you will find systems that are approximated as an anharmonic oscillator. One common example is a superconducting qubit. So this is one of the most famous ways that people are trying to build quantum computers using superconductivity. And the way that is done is using something called a Josephson junction. I'm not going into the details of what that is, but basically a Josephson junction plus a capacitor can form an anharmonic oscillator. And you can control the anharmonic oscillator to keep the electron in its like ground and first excited state 0 and 1 and treat it like a qubit. Whereas a normal LC oscillator, that's not possible. So that's why superconductivity was used there. And it is one of the common ways of building a quantum computer. It has its benefits and its drawbacks. A third way to define a qubit could be using light. Photonic quantum computing is also very popular. I believe Zandau is a company that's exploring that a lot. And you can use two different states of light as the two qubit states. One example is different polarizations of light. You might remember vertical and horizontal polarization of light. So you can use those two as the two states to define a qubit. So once we have defined a qubit, we also need to make sure that we can entangle qubits and form states like the Bell states. We saw that this entanglement and Bell states is very important to do all sorts of computations. And to get qubits to couple is not as easy as it sounds. Like it's tricky because you need to let some sort of electromagnetic interaction or something happen between them. Meaning, imagine you have one qubit, you can isolate it completely and control it. So that is cool. But if you have two qubits, you need to let them interact with each other. At the same time, you cannot have environment coming in between and causing noise. So that is a bit tricky. So, but our system needs to allow coupling because without that, we cannot do half the operation, most of the operations in quantum computing. So the third point required is stability. This is probably the most important. So if you have classical bits of information, they are very stable. You can store it in some memory and just forget about it. Years later, you can open that memory, it will be safe. Nothing's going to happen. Quantum states are not so stable. They are very, very, very susceptible to noise. So the way we measure how stable something is using a time called decoherence time. Basically, it is how long a state will be in like the state we left it in before we can no longer identify. Let's say we leave a state in the zero state. Like after some time, if we leave it for a long time, suddenly it will be in some superposition of 0 and 1 and we lose our original information. How long it takes is called decoherence time. This is probably the biggest challenge. One way to increase the decoherence time is to go to very low temperatures. Thereby outside environmental disturbance and all reduces. So that's why you will be looking at quantum computers at like 2 Kelvin, 3 Kelvin. We need super refrigerators for all that. This is the reason, because we need to reduce noise as much as possible. So this is again a table from quantum computing textbook. TQ is the decoherence time, and you can see that all of them are in like fractions of a second. These are ballpark, so don't take them with a pinch of salt, but just to give you a scale of what we are looking at, these qubits are only stable for fractions of a second. So the next thing is we need to be able to operate on them. We need to be able to implement a full set of unitary quantum gates. And again, we need to also be able to implement multiple qubit gates like the C0 gate. This is trickier to implement because you're operating on two qubits at the same time. So to be able to design this is tricky. Another point to keep in mind is these operations cannot take too long as well. So the time scale of the operation is important. That's defined in this table by T operation. So with the time a qubit is stable and the T operation, if you take the ratio, you can tell us like roughly how many operations can be operated on a qubit before it loses stability. And that is a pretty important number. This is for different systems. Again, take them with a pinch of salt just to give you a ballpark idea of what these numbers look like. So that is all I wanted to mention about how to build quantum computers. And towards the future, there is a lot of research and engineering going into this. A lot of universities, but also a lot of companies see profit possibilities. Like they think quantum computing can become viable. It's important. Like you can see companies in all sorts of fields. Finance companies, a few of them are starting to like look into the viability of quantum computing. Banks need to look into it because it affects their encryption. There's something called quantum cryptography. Software companies obviously want to build quantum computers. Automobile companies are seeing if they can use it anywhere. In terms of companies that are building quantum computers, IBM, Google, Xandau are examples. This is not sponsored in any way. It's just what I've heard of and I'm mentioning to you. And also, if you've not heard of, there's something called Qiskit. So Qiskit is an open source quantum computing software available on the internet for anyone to use. It is IBM's property and it's pretty cool. If you want to try quantum computing, try to build actual circuits and stuff, you can do it with Qiskit. Just Google this later if you're seeing this for the first time. It's actually very cool. And yeah, this is what one of the quantum computers that Google has, the first one you picture with Sundar Pichai. And yeah, you can see this whole complicated whole structure. The red thing is probably for refrigeration and all of these wires, and this thing is to entangle the different qubits. Yeah, pretty cool stuff. And this is like a development roadmap that IBM put up. So right now they have their best quantum computer, I believe, is Osprey, which is a 433 qubit quantum computer. And later this year, they want to be able to develop Condor, which is a 1100 qubit quantum computer. And slowly they believe that they can push into thousands and 10,000 of qubits eventually by 2030. And they have a lot of other ideas as well. So this is companies, at least they believe that this could be something very practically useful in the future, and they are building towards like making quantum computers. And yeah, there is a lot of funding and research going into this. So that is it on how to build a quantum computer, very brief. And I wanted to end these two sessions with a little bit of a philosophical discussion. And we do that through Bell's inequality. And we're going to see something that Einstein couldn't believe. He attacked quantum mechanics and said this is not a complete theory of the world. But then some people came up with a way to test this, and they showed that what Einstein said was completely wrong. And yeah, we will look into that now. So this is called Bell's inequality. So Einstein, Podolsky, and Rosen, EPR, the three scientists together wrote a paper where they suggested that quantum mechanics is an incomplete theory. It said that actually these systems, these particle systems and all, have some elements of reality, is something what they said. That is, there is some, like for example, spin, there is actually some spin measurement there that we are not able to measure. And we just find out and change the state, but they're actually there. It's not like the state is actually a superposition state and it decomposes at the last minute, like decomposes only during measurement. There is actually some element of reality that tells the system what we are going to get from measurement before we do it itself, is what Einstein suggested. So scientists managed to come up with an experiment to test if really these measurements are pre-decided and that just we are not able to find them out, or whether it's actually like the quantum mechanical way of thinking where it's in a superposition state and it actually really just decomposes based on a probability, based on luck. So I'll tell you what this experiment is. We are returning to our friends Alice and Bob. So consider first that we are doing a classical experiment on two particles. Alice has one particle and Bob has the other. So Alice and Bob can make one of two measurements, okay? Each. Let's call these measurements Q, R, S, and T. So Alice randomly flips a coin and decides whether she's going to do Q or R. Bob flips a coin and is going to decide whether he's going to do S or T. So the results of these measurements can be plus or minus 1. So if Alice measures Q, she can get either plus 1 or minus 1. If Alice measures R, sorry about that, she can get either plus 1 or minus 1. If Bob measures S, similarly, he can get plus 1 or minus 1. If Bob measures T, he can get plus 1 or minus 1. He and both of them randomly flip a coin to decide which measurement they are going to make. Okay, this is all classical. Now consider QS, which is the product of the like what value you get for Q and what value you get for S, plus RS plus RT minus QT. So, for example, if Q is 1, R is minus 1, say S is 1, T is 1, then QS is 1, then RS is minus 1, and RT is minus 1, minus QT is minus 1. So it totally adds up to minus 2. So this value will give us minus 2. Like that, based on the values, we can calculate QS plus RS plus RT minus QT. But we can also simplify Q. We can take S common here and T common here and write this as Q plus R times S plus R minus Q times T. So why do we write it like this? Because Q and R are both, Q comma R are both equal to plus or minus 1. So Q plus R is either 0 or plus or minus 2. It is one of these values only. So that means either Q plus R is equal to 0 or R minus Q has to be 0. Right? For example, if Q is 1, then R can be plus 1 or minus 1. If R is minus 1, Q plus R is 0. If R is plus 1, R minus Q is 0. So one of these two have to be 0, regardless of the value, actual value of R and Q. So one of these two is 0, and the other value is going to be 2, plus or minus 2. And the thing it's multiplying is plus or minus 1. So that means this entire thing is going to multiply and give us plus or minus 2. I'll just go through the logic one more time. We can simplify into these two terms. One of these two terms has to be 0 because Q plus R or R minus Q has to be 0. And the other term, the bracket is 2 and the outside bracket is 1. So it's going to give plus or minus 2. So since this value is always plus or minus 2, let's take the expected value. That is, let's repeat this experiment a lot of times. And what is the average that we are going to get? That is the meaning of expected value. So the expected value of QS plus the expected value of RS plus the expected value of RT minus the expected value of QT has to be less than or equal to 2. Because if each and every value can only be plus or minus 2, then the average cannot be greater than 2. So this is called Bell's inequality. This is one of Bell's inequalities. Now, this is a classical experiment, and for this experiment, we are showing this inequality. Now consider a quantum mechanical experiment of the same nature. So we have a Bell state psi 0, 1 minus 1, 0 by root 2. Then let Z and X be the measurement of spin in the Z and X direction respectively, 2 times that, because we want plus or minus 1, 0. So if you measure Z, its spin plus half, you will get 1. If it's spin minus half, you'll get minus 1. X is the spin in the X direction. If you measure, you'll get spin. If it's plus half, you get plus 1. If it's minus half, you get minus 1. So just 2 times the spin in Z and X direction. So with that, the definitions of Z and X, these are our 4 operators, Q, R, S, and T. Q is just finding the Z spin of the first qubit. R is just finding the X spin of the second qubit. S is a superposition of Z and X. So you measure both of these and add this, find this S, and this is T. Okay. So with this definition, let's calculate the expected value of what we saw. We saw this expected value cannot be greater than 2 for a classical experiment. Quantum mechanically, what is the expected value of QS? So QS is nothing but just multiply the 2 operators. So you get Z1, Z2, and you get minus Z1, Z2 and minus Z1, X2. Now, what is the expected value of Z1, Z2? Now let's look at this qubit. If we measure the Z spin of one qubit, whatever we get, the Z spin of the other qubit is going to be the negative of that. If the Z spin of the first qubit is 0, then the Z spin of the other qubit is going to be 1. So if it's plus half, it's going to be minus half. So plus 1, minus 1. So the product of Z1, Z2 is always going to be minus 1. And minus Z1, Z2 is always going to be 1. So the expected value of minus Z1, Z2 is plus 1. It's always going to be plus 1. Now let's look at the expected value of minus Z1, X2. So if you measure Z1, if you get 0, the second qubit decomposes into 1. If you get 1, the second qubit decomposes into 0. the expected value of measurement of x for both of these is 0 because they are equally likely to be spin plus half and spin minus half, right? Because you're measuring x on z basis states. Again, the fact that we did spin half systems yesterday really helps us here. So since that expectation is 0, this expected value is 0. So we can calculate the expected value of the total to be 1 by root 2, expected value of QS. Similarly, we can calculate the expected value of RS, RT, and QT using these definitions here. I'm not doing that, but basically, when we multiply the Z1, Z2 minus Z1, Z2 is minus Z1, Z2 is 1, and any Z1, X2 or X1, Z2 will be 0 expected value. So, and each of these multiplications, QS, QT, RS, RT, all have one Z1, Z2 and one X1, Z2. So the X1, Z2s go away, the Z1, Z2s remain. So that's why all of them have 1 by root 2. QT alone has a Z1, Z2 instead of a minus Z1, Z2. So that's why its expected value alone is minus 1 by root 2. So now, since we have the expected value of all four, let's add them up. So we have 1 by root 2 plus 1 by root 2 plus 1 by root 2 minus of minus 1 by root 2. And this gives us 2 root 2, which is greater than 2. So quantum mechanics tells us we can define a measurement that breaks Bell's inequality. But Bell's inequality tells us that if the measurement is predetermined, if there were predetermined values of Q, S, R, and T, we cannot get greater than 2. Like if we perform this experiment hundreds of times and we test this experimental value, this expectation should not be greater than 2. But quantum mechanics tells us this expectation should be 2 root 2. And so people actually performed a variation of, like a version of this experiment. Again, I'm not going into the experimental details, but basically this. And they wanted to find out which way of thinking is correct. And well, quantum mechanics wins out. The expected value was 2 root 2, which means Bell's inequality does not hold. The classical way of thinking does not hold. And what Einstein, Podolsky, Rosen had pointed out, that was wrong. And that quantum mechanics can be a complete theory as well. Can be a complete theory of nature. And this sort of local realism that Einstein was suggesting, that there are some local measurements that predefine what we are going to get from our measurements. There's some local values that we don't know. That theory cannot hold. This was experimentally proven. And another reason why all physicists, even though it sounds so weird, so unclassical, so not what we're used to, like quantum mechanics sounds like that, everyone still agrees that quantum mechanics is the real theory of the world we live in. And that's why we study it. And that's how we're going to use it to hopefully perform awesome computations in the future with quantum computing. And with that, I'd like to end the two sessions to say that, yeah, quantum mechanics and quantum computing is very different from anything we've seen before. So it is counterintuitive in that sense, but it's not like it's some illogical mess or sham or anything. With some math, with some practice, there is it's just a new way of thinking that we have to adapt and get used to. And once we get used to, it can be very intuitive and very cool. So that's where I'd like to end. So yeah, that's it from me. So we can have any questions for like 5-10 minutes and we will end there. Thanks everyone for attending both sessions. Yeah, thanks. And if you have questions later, post them to us. We'll try to answer them. That's great to hear. Just call me Sai. Please don't call me sir. I'm just a student kid like you all. Yeah, we will share the slides for both sessions. Yep. Attendance, I believe Ganesh will take based on the recording or based on this. Ganesh, can you
Yeah, it
confirm?
is. Yeah, it is recorded.
Recorded, so he'll take the attendance. Don't worry about it.